Hello everyone, and welcome to Physics 2211, Principles of Physics 1. I will be your instructor for this course. My name is Jim Gwynn. Hopefully you've already gone through your syllabus and have asked your instructor, whether it's me or someone else, any questions that you have. So we are just going to dive right into the content. Today we are going to cover Section 1, Mathematical Introduction, and we're going to start with significant figures. Perhaps you've already talked a little bit about this in maybe one of your other classes, but we're going to go over it a little bit more for now. One of the important aspects of physics is that it is a quantitative science, and what that means is that physics uses many very careful measurements of all sorts of different kinds of quantities. Those measurements very often involve numbers. So it's going to be very important for us to make sure we understand what we mean by the numbers that we use. That might seem a very obvious thing to say, but there are some subtleties about numbers that I want to talk about to make sure that we always know exactly what we're talking about. For example, if we were to say something was 6, just imagine that we use this number 6 to describe something. Maybe I measure the length of a table and I say it's 6 units long or whatever, something like that. What do we mean, when we say 6? Well, what we are going to mean in this course is that that measurement of whatever that is, 6 of something, the value of that measurement we expect, we hope, is closer to 6 than it is to, say, 5. If the measurement were actually closer to 5, we would hope that we would say the value is 5 rather than 6. Likewise, we hope it's closer to 6 than it is to 7. 8, 9, 4, 3, those are right out. So what we will say is that when we say something is 6, we mean some kind of quantity that's closer to 6 than it is to 5, and closer to 6 than it is to 7. Kind of a general rule of thumb is we expect that the value that we are stating is somewhere in between some range, maybe around between 5.5 and 6.5. If the value were a little bit less than 5.5, hopefully we would say it was 5. If it were a little bit bigger than 6.5, hopefully we would say it were 7. So we're going to say something in between 5.5 and 6.5. In other words, say 6 plus or minus a half. In other words, 0.5. 6 plus or minus 0.5. We're not always going to write this. What we'll just write is 6. But let's keep in mind that we mean some approximate quantity. If this is coming from some measurement or perhaps from some calculation, rarely do we know these values exactly. There are some situations where we will, and I'll come back to that later on. But usually the values that we use, we are talking about some approximate quantity that we are stating as best as we can, as precisely as we can. Now, this is going to be very similar to larger numbers or smaller numbers. So, for example, if I were to say something like 26, what I really mean is something, in between 25.5 and 26.5. In other words, 26 plus or minus 0.5. 1/2 of this smallest digit in the ones column, you might say, in this case, of the value that is stated. If we were to say something like 32.6, now we're giving the tenths place, so the uncertainty, you might say, would be on the next place, the hundredths place, 0.05. If we were stating some very large number, like maybe 12,000, then the uncertainty would be in this next digit, the zeros. Are these zeros important or not? We'll come back to that. Let's just, for the moment, assume they're not. Then this would be 12,000, say, plus or minus 500. In other words, it's closer to 12,000 than it is to 11,000, closer to 12,000 than it is to 13,000. Okay, so that's the general idea of what we're talking about. we are not always going to include these written uncertainties. We want to just always assume that they're there. The quantities that we'll be using are not typically exact quantities, but approximate quantities. Now, let's imagine that we send out 4 people to measure some distance outside, say the distance from our classroom to someplace down the street. And let's say they come back and they quote some different values. One person quotes a distance of, let's say, 2,000, and I'm going to stick in a unit here, meters. I'll come back to talk about units in just a minute. Say 2,000 meters. Another person quotes a value of 2,100 meters. Another one quotes a value of 2,130 meters. And another person, I don't know how exactly they calculated this or measured this so precisely, but they say 2,132 meters. Now, what is the difference between these 4 values? Excuse me. Well, we would say that these have different precisions, and a very easy way of talking about the precision of a number is how many significant figures it has. We will say that this number, 2,000, has 1 significant figure. 1 significant figure. And I will sometimes shorten this to sig fig, and sometimes even shorter to just SF. 2,100, we would say that has 2 sig figs. 2. 2,130, we would say has 3 sig figs. 2,132 has 4 sig figs. Now, we might even have more, like 2,132.7. That would have 5 sig figs, or 0.78. That would have 6 sig figs, etc., etc. So we talk about the precision of a value in terms of how many sig figs, how many significant figures that quantity has. Now, let's keep in mind, what do we mean by these numbers? This would be, say, plus or minus 500 meters. This would be, say, plus or minus 50 meters. This one would be plus or minus 5 meters. This would be plus or minus 0.5 meters. Notice that the uncertainty, or the amount that we don't know about the value, gets smaller the greater the number of significant figures in these particular numbers, okay? The smaller the last significant digit is, the greater the precision, or the more precisely we know those values. Okay. Now, let's go back to these zeros. Are zeros significant or not? Well, that depends. There are 3 rules that we will keep in mind as to whether zeros are significant or not. Let's go over those one at a time. The rules for zeros. Rule number 1. Zeros to the left of all non-zero digits are never significant. We're going to break the digits that we use, the numbers that we use, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, into 2 separate groups. There's 0, and then there are the non-zero digits. Non-zero digits are always significant. Anytime you have a non-zero digit, 1, 2, 3, 4, 5, 6, 7, 8, 9, it is significant. What about the zeros? Well, let's imagine we have a number like 0.00, I'm just matching these to the notes, 0.023. The 2 and the 3, those are non-zero digits, those are significant. But these zeros are to the left of all of the non-zero digits. See, here are the non-zero digits. These are to the left of those. They are not significant. So how many sig figs does this quantity, 0.0023, have? It would have just 2 significant figures. Okay, what about, let's say, 0.000000000367? Well, 3, 6, 7, those are all significant, so there's 3. All of these zeros are to the left of the non-zero digits, and so they are not significant. So this quantity, even though it's very, very long, has only 3 sig figs. Doesn't matter how many zeros there are, 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 4, that still only has 1 sig fig. Okay? Great. There is rule number 1. What about rule number 2? Rule number 2. Zeros between non-zero digits are always significant. So, for example, what about 104? Well, the 1 and the 4 are non-zero digits. Those are always significant. This 0 is between non-zero digits, so it is significant. So how many does this one have? 3 sig figs. 3 sig figs. 2, 3, 0, 0, 4, 6. Again, the 2, 3, 4, and 6, non-zero digits, they are significant. These zeros are between non-zero digits, so they are significant. It doesn't matter how many there are in a row, they will all be significant. So how many does this one have? 1, 2, 3, 4, 5, 6. 6 sig figs. And it doesn't matter if there's a decimal point in there, nor if there are different groups in between non-zero digits. So for example, 5, 0, 5, 0.003. The 5 and the 5 are non-zero digits. This 0 is in between non-zero digits. It is significant. 5 and 3, non-zero digits. These zeros are in between non-zero digits. They are also significant. It does not matter if there's a decimal point in there. All of those are significant. So how many sig figs do we have? 1, 2, 3, 4, 5, 6, 7. 7 sig figs. Okay, so there is rule number 2. What about the last one? Rule number 3. Rule number 3. Now, we've talked about zeros in between digits, to the left of non-zero digits. What about zeros to the right of non-zero digits? Rule number 3. Zeros to the right of all non-zero digits are significant only if there is a written decimal point present. All right, let's take a look at some examples of this. What about 1,300, 1300? Well, 1 and 3, significant. These zeros are to the right of the non-zero digits, but there is no written decimal point present. Therefore, they are not significant, so that only has 2 sig figs. 65000 point. These zeros are to the right, but now there is a decimal point present, and that makes all of the zeros significant. So 65 and then 0005 sig figs. 39.00. Again, there is a decimal point present. That makes all of the zeros significant that are to the right. It doesn't matter whether the zeros are to the left of the decimal point or to the right of the decimal point. They are still significant. So 39.00, how many? 4 sig figs. If this were 390.0, still 1, 2, 3, 4. Still 4 sig figs. And give you one more. This one's in the notes. 60.000. Again, we've got a 6, significant. zeros to the right, there is a decimal point present, so they are all significant. 2, 3, 4, 5, 5, 6, 6. Okay, very good. Sometimes we are going to have numbers that are so large, for example, like if we were to have a number like 27,000,000 with just a whole bunch of zeros, or numbers that are so small, for example, 0.000000000027, that there's a way of writing these to make sure that we will keep track of exactly how many zeros there are in there, and that is to use a form that is called scientific notation. So let's take a look at that.